Good morning, or good afternoon, or good whatever time it is where you are. Last week we looked at random walks as an introduction to simulation and stochastic programming. We looked at things quite informally. Now I want to lay down some of the foundations we need to understand stochastic situations more rigorously. Before I do that, I want to start with a little bit of philosophy. There's something very comforting about Newtonian mechanics. You push down on one end of a lever and the other end goes up. You throw a ball up in the air, it travels a parabolic path and then comes down. When we first learn about physics, we learn the lovely equation F equals ma. In short, everything happens for a reason. The physical world is a completely predictable place. All future states of a physical system can be derived from knowledge about its current state. For centuries, this was the prevailing scientific wisdom. And then along came quantum mechanics and the Copenhagen doctrine. It's amazing for such a remarkably pretty city that it could be the home of such a deeply disturbing concept. The doctrine's proponents, led by Bohr and Heisenberg, argued that at its most fundamental level, the behavior of the physical world cannot be predicted. One can make probabilistic statements of the form X is highly likely, but it would be inappropriate, they argued, to make statements of the form X is certain. Other distinguished physicists, most notably Einstein and Schrödinger, vehemently disagreed. Eventually, after much discussion, it boiled down to the question of whether the world was causally non-deterministic, that is to say, not every event is caused by previous events, or predictively non-deterministic, that is to say, the lack of knowledge about the world makes it impossible to make accurate predictions about the future states. Einstein summed up his notion of predictive non-determinism beautifully. Quote, "The essentially statistical character of contemporary theory is solely to be ascribed to the fact that this theory operates with an incomplete description of physical systems. That is to say, he believed the world would be predictive if only we could understand it better." The question of causal non-determinism is still unsettled. However, whether we cannot predict events because they are truly unpredictable or because we don't have enough information to predict them is not usually of practical importance. Let's look at a simple example. I'm going to ask you, yes, you out there, is today your birthday? Now, there's nothing probabilistic about the answer to this question. You know whether today is or isn't your birthday. And by the way, if it is your birthday, why are you spending it listening to me? Anyway, I don't know, however, so even though there's no randomness here, I have to treat it as if it's random, and the best guess I can make is that the probability of it being your birthday is a little bit less than 1 out of 365. Why a little bit less? Well, we do have to think about leap years. While the Bohr-Einstein debate was about how to understand the lowest levels of the physical world, the same issues arise at the macroscopic level. Perhaps the outcomes of horse races, spins of roulette wheels, stock market investments, and baseball games are causally deterministic. However, there's ample evidence that it's pretty dangerous to treat them as predictably deterministic. Of course, that won't stop some of you from losing lots of money because you believe otherwise. Okay, that gets us back to stochastic processes. We looked at this last week. To remind you, a stochastic process is any process where the next state might depend on both the previous state and some random element. Let's look at a couple of specifications to illustrate the point. Both of these specifications are for a function for rolling a die. Actually, not 2 dice, but 1 die. The first one says roll die should return an int between 1 and 6. This specification would allow a non-deterministic implementation, but not require it. It would be okay to always return 2, or to always return numbers in the sequence 1, 2, 3, 4, 5, 6. The second specification, on the other hand, insists that roll die be non-deterministic, i.e., we cannot predict the number that it's returned. So here we have something that's called underdetermined. The specification doesn't tell us exactly what it does, but here we have something that's genuinely non-deterministic. As we've already seen, Python includes simple ways to write programs that use randomness. Let's consider the following simulation of rolling the die. We have that over here. So I've got roll die at the top. This looks exactly like what we looked at last week, where we used random.choice. And then roll n, which merely calls roll die n times and returns the result of the numbers returned as a string. So for example, if I print roll n5, I get a random string 32316. I can try it again, and presumably I will get a different string. We can see it's a string, by the way, because when I type it from the shell, we see the quote signs around it. Now I want to ask you another question. When I call roll n, would you be more surprised if it returned 5 ones or some more random looking sequence, 5, 4, say 3, 2, 4? Which of these is more random? Well, it's a trick question. Each of these is equally likely because the value of each roll is independent of the previous rolls. That is to say, the fact that I rolled a 1 the first time has no impact on whether or not I will roll a 1 the second time. Two events are independent if the outcome of one event has no influence on the outcome of the other. So now that we know that each of these is equally likely, we can ask the question, how likely are they? So for example, how likely is it that we'll get 5 ones? In general, when we talk about the probability of a result having some property, for example, being all ones, we are asking what fraction of all possible results has the property? That tells us that we need to start with the question, how many different sequences are there of length 5? Earlier in the course, we looked at binary numbers, and we saw that given n binary digits, there were 2 to the n possible binary numbers. When we looked at decimal digits, we saw that it was 10 to the n. And now, with the dice, we're looking at digits base 6. So the number of possibilities are going to be 6 to the n. So for a 6-sided die, there are 6 to the 5th possible sequences of length 5. That tells us that the probability of rolling 10 consecutive ones should be 1 over 6 to the 5th. A pretty small number. It's approximately equal to 0.001286. Or, a simpler way to think about it, 1 out of 7,776 possibilities. Pretty low, but no lower than the probability of any other particular sequence of 5 rolls. Let's look at a simulation to check this. So I'm going to use roll n and roll, which uses roll die to do the simulation. Get target takes a goal, which is a string, for example, 5 ones, and then we'll roll the die that many times, the length of the string, and we'll do this over and over again until it gets a string of 5 ones. Well, if I call the goal ones. And when it's done, it will return the number of attempts it took to reach the goal. Run sim calls get target multiple times, and you'll remember from last week the importance of using multiple trials, and then gets the average number of tries it took to reach the goal, divides 1 by that number to get the probability of any single try being that goal. Let's see what happens if we run it for 5 ones. We're now going to run the simulation and see whether we get the answers we expected. Just so you can remember what we expected, maybe I should print the probability. And we calculated it to be roughly 0.000126. So now we'll run these and see what we get. Okay, we got 2 different answers. We'd expect that. Remember, this is randomness. We'd also expect that neither answer is exactly what the calculated probability was. After all, we only did 100 trials, but both are pretty close. They're in the right neighborhood, which should give us some confidence. I've run this with much bigger numbers than 100 trials, and as you might guess, the more trials I use, the closer we get to the actual probability. Let's go on now and look at a different problem. Suppose we want to know the probability of rolling the die 5 times without getting any ones. So 5 rolls, no ones, as opposed to all ones. One way to answer this question is to think about how many of the 6 to the 5 possibilities don't contain a 1. We can compute it as follows. On the first roll, the probability of it not being a 1 is going to be 5 out of 6, any side of the die except the 1. If we think about not rolling a 1 on either the first or the second roll, it's going to be I didn't get a 1 on the first roll, and I didn't get a 1 on the second roll. I can multiply that, and not getting it in either of the first 2 rolls will be 25/36. Notice, by the way, that this is a smaller number than this. That's exactly what we should expect. After all, the probability of not getting it twice and with 2 rolls ought to be smaller than the probability of not getting it with 1 roll. So if we want to think about not getting it in any of the 5 rolls, what should it be? 5/6 to the 5th. How about the probability of rolling at least 1 1? Well, we know the probability of getting no ones in 5 rolls is 5/6 to the 5th. We know that the probability of getting at least one of the many possible rolls is 1. So we know that the probability of getting at least 1 1 must be 1 minus the probability of getting no ones. That is to say 1 minus 5/6 to the 5th. Let's look at one more problem before wrapping up this segment. Imagine that instead of watching this recording in the comfort of your home, you are watching me live in a packed classroom with 99 other students. Imagine further that if today is somebody in the room's birthday, I'm going to give them $10. What's the probability that I have to open my wallet? Well, in order to compute this, we need to make an assumption about birthdays. And that assumption is that the birthdays are uniformly distributed. And to simplify my life, I'm going to say they're uniformly distributed over 365 days. This may not be true. Maybe more kids are born in July than in January. I don't actually know. But we'll assume that every birthday is equally likely. So if I look at those 100 students and I choose 1, the probability of today being that student's birthday is 1/365. Now if I take a second student, the probability of it being that student's birthday is also 1/365. Can I just add those two to get the probability of it being one of their birthdays? Absolutely not. Think about it. Suppose I had 500 students in the class and I added them all up, then I'd get the probability of it being somebody's birthday was 500/365, which is impossible because we know that probabilities always have to be less than or equal to 1. So how do I do this? I use the -1 trick. It's a trick we just used. The probability of it not being the first student's birthday is 364/365. The probability of it not being the second student's birthday is the same. And so if I look at 100 students, the probability of it being none of their birthdays is 364/365 to the 100th. And I just have to subtract that from 1 to discover the probability of it being somebody's birthday. And as it happens, that's about 0.24. Not so unlikely that I'm going to get stuck.